Hi, welcome back. And today I'm going to cover deep learning concepts. If you are not familiar with machine learning and you haven't seen my video yet, I'm going to put the link in the description below. So I will pick up where we left off last time. Last time we talked about regression analysis and classification. And I concluded with the general process of training a model in machine learning. The general process goes as follows. You start with a data set, the one you see above here. You split your data set in three parts: a training set, a validation set, and a test set. And then you visualize your data. Once you visualize your data, you see what are the correlations. You see if there are some things that you recognize in the data, some correlations that you know from before. And it will help you design your feature space. Once you design your feature space, you can now tune your hyperparameters. You go from hyperparameters to optimization. You run your stochastic gradient descent algorithm. And then once you get your optimal predictor, you test it on your validation set. If you're not satisfied with your loss, you go back to redesigning your feature space or your feature vector, and then you repeat that process again and again until you're satisfied, and you test now your generalization error, or you test your model on your test set to see if it actually generalizes. Now, as we mentioned last time, this process is pretty hectic, especially if you need to design your feature vector every time. The nonlinearity in your model really comes from the choice of phi. And the big question would be, can we automate this feature extraction? Can we come up with an algorithm that automatically discovers these features on its own? And this is the motivation for using deep learning. Deep learning promises to do that on its own, and as we'll see in this lecture. All right, so let's go back to linear predictors. What are linear predictors? Linear predictors are given by this equation, fwx equals w dot px. Now, as we said, w is a set of fitting coefficients that we want to discover using our learning algorithm. And phi, our feature vector, can be designed. These are examples of phi where we can add a bias to our linear predictor. We can add a polynomial. We can design it to be a polynomial or even a sine function or anything you want. You just drop it into this feature vector. But I assumed in the previous video that x and y are one-dimensional input to one-dimensional output. But this doesn't have to be the case. X can be any dimension, and y can be any dimension. If that's the case, then our linear predictor becomes like this. Fwx equals a matrix w times phi x. Now phi takes this n-dimensional vector, where here I say it's n by 1, and maps it, or it actually takes, well, it takes x, which is any dimension, and maps it to n dimensions. And now w will be m by n and multiplies phi x, which is m by n and n by 1, which makes now our prediction to be m by 1. So it becomes a matrix multiplication problem. And of course, here w will be our fitting parameter. It will be a fitting matrix. And all the entries in the matrix are fitting parameters that we want to discover using learning algorithm, like stochastic gradient descent. Again, a visualization of that would be the same. Before we had one-dimensional x mapped to one-dimensional y. But if it's higher dimensions, you can imagine that this plot will be a higher dimensional space, where x or phi x will be n dimensions, and there's sort of a hyperplane that maps phi x to y. OK, y here, there's something we're going to change notation a bit to make things a bit simpler. But I hope it's not very confusing. Instead of using phi x, I'm going to use x. And the idea is that you take your input x and you change it by you yourself choose what phi is. And now your new input space is phi x. So I'm just going to call that x, your input. Your prediction now is going to be fwx, and instead of using fwx, I'm going to use y hat, your prediction. It's just a notation for your prediction. All right, so linear predictors. Let's come back to defining linear predictors and dive deeper into what it means to have this matrix multiplication. So the representation of a linear predictor with matrix multiplication is y hat equals wx. An index notation that sort of shows what operations are happening in this matrix multiplication is to simply take every component yi hat of the vector y hat and set it equal to the sum of wij xj. And the sum goes from j equals 1 to n. And this is sort of an index notation. Now, there is another notation that's not as common in math, but is kind of common representation in neural networks, which is the network representation, or sort of a graph representation. Let's say x is three-dimensional. So it has three entries, x1, x2, and x3. And now we take x1, x2, x3, and we multiply it by the first column of w. That would be row of w. So we have wx, so we take the first row of w and multiply it by x. And the first row of w is w11, w12, and w13. So to get the first element of y hat, what we do is w1 times w11 plus w2 times w12 plus w3 times w13. This is a simple matrix multiplication. And then we sum these equals to the first element. You do the same thing with the second element. And now it would be w21, w22, and w23, which will give you the second element, y hat 2. Now, you might say, why use this complicated representation? And this is a good question. There is no reason to use it, but it's common in neural nets. And graphical representation is sometimes useful to visualize things. It's all the same. These three representations are represent the same thing. It's a matrix multiplication. There's one thing that I skimmed over, which becomes useful in neural nets. There's this assumption that you have to add a bias. So the idea is that this matrix multiplication, I can add a bias to this matrix multiplication to shift it from its origin. One way to account for the bias is to impose the first element in this vector when we create this feature vector. To choose the first element to be 1. And in that sense, we make the first element a bias. OK. Let's move on and talk about nonlinear predictors. One example of a nonlinear predictor is to take this matrix multiplication, wx, and to apply a nonlinear function to it, sigma. Now, sigma can be any nonlinear function. But this graphical representation now would look something like this, where we take x1, x2, x3, we multiply it by w. And then after we do the summation, we apply a nonlinear function sigma, and we get y1 hat and y2 hat. In the specific case where sigma is a logistic function, like here, this would be a logistic regression problem, or a classification problem, in fact, something that we sort of mentioned last time. And in this case, the logistic function looks like this graphically, as shown there. And if you look at a classification problem where you have inputs x1 and x2, then you want to classify these green dot or yellow stars. In this case, the classifier will give you either will give you a value between 0 and 1. If you're on this side, you're going to be 0. If you're on that side, you're going to be 1. And it goes smoothly between 0 and 1. And the output of this predictor will give you the probability of being either 0 or 1. If you're above 0.5, you're going to be closer to 1. If you're below 0.5, you're going to the prediction is close to 0. So this is logistic regression, something that I mentioned quickly last time. But in neural networks, this is a common activation function. So this is called an activation function, sigma. And this activation function doesn't have to be a logistic function. It could be any other nonlinear function. It takes this linear transformation, wx, and it shapes it or deforms it in some nonlinear way. So this is called a rectified linear unit, where is also common in neural networks. But the idea is that here you can actually put in any nonlinear function, and these have different properties and different advantages in your learning procedure. So you can see this is simply 0 for x smaller than 0, and it's sigma of x equals x for x greater than 0. All right, so this is a nonlinear predictor. So what is a neural network? Now we're ready to understand what neural network is. It's simply a concatenation of nonlinear predictors. So here we took wx, and we applied a nonlinear function sigma to it. Now we take this output, and we apply a linear transform to it, again, another w. So here, the first one would be w1, the second one would be w2, and we apply another nonlinear function to it. This graphically looks like this now. So we take x, we multiplied by w1, and then we apply sigma, a nonlinear function, and then we get v, some variable v. We apply another linear transform to it, w2, and then we apply sigma. We get finally the output y hat that we're looking for. You can now understand basically that neural networks are a concatenation of linear and nonlinear functions. So it's a composition, in fact, a mathematical composition of functions where you have linear, then nonlinear, then linear, then nonlinear function. You can actually, it makes more sense, and it's clearer to call it a linear, nonlinear, linear, nonlinear function than it is to call it a neural network, because it's more descriptive of what it actually is. And this linear, nonlinear, linear, nonlinear function takes in an output x and returns, takes in an input x and returns an output y hat. So to simplify the representation a little, I just redrew the neural network in this way. And now we have x multiplied by w1, apply sigma, v multiplied by w2, apply sigma, you get y hat. And sometimes you see this notation where you have v equals sigma w1x, and then y hat is actually equal to sigma w2v. So there's two stages of computation, of linear, nonlinear computations. This middle layer, which I didn't say how I chose it to be two-dimensional. So we assume that the input is three-dimensional and the output is two-dimensional. This is something that you get from your data. For example, if you have an image with 1,000 or 10,000 pixels, it's specified this will correspond to your dimension of x. And then the output, let's say, is binary. It's either on or off. That would be one-dimensional. In this case, it's two-dimensional. But the middle layer, how do we choose the dimension of the middle layer? And this is something that would be part of your hyperparameters. Or it depends on your problem, and it's something you have to choose. That's not clear from the data itself. And this middle layer is called the hidden layer, because it's not something that you're interested in as an output in itself. Sometimes you are, as I will mention later. But it's a hidden layer because it's neither the input, neither the output, nor the output. And this hidden layer is the key in neural networks. The idea is that these hidden layers can actually perform this automated feature selection for you. It can be interpreted as the phi of x that we spoke about earlier. Instead of you designing the features yourself, the algorithm on its own will figure out how to map x to phi of x in the most optimal way to get the best prediction y hat. This is not always the case. Networks will not always do that kind of feature selection. And sometimes these hidden layers will give you outputs that you cannot interpret. And this is a tricky problem that we will address later. Deep networks. So we said what a neural network is. What is a deep network? Well, it's simply a neural network with many layers, with many hidden layers. So now this is an example of a deep network where I added one extra layer. And then one extra layer will look something like this, where you have x, it maps to some hidden layer v1, and then it maps to another hidden layer v2, and finally to the output y hat. And now you can write this again in terms of these operations, the sequence of these operations. So this is all a deep network is. And you can imagine that you can concatenate as many hidden layers as you want. In fact, real-world deep networks have hundreds, sometimes hundreds of hidden layers. The choice of these hidden layers, the dimension, for example, this is two-dimensional vector, and v2 is a four-dimensional vector. How do you choose the dimension of these vectors is really sometimes something that you have to try out. There is no, sometimes it comes from intuition, sometimes it depends on your problem, and you know, for example, that you want to take an input x and compress it to a lower dimension. So you choose v1 and v2 to be lower dimensional. Sometimes you want to project it on a higher dimension, and therefore you choose v1 and v2 to be higher dimensional. Once you when you start to experiment with neural networks, you start to sort of have an intuition on how deep you want your network to be and what are the dimensions of these hidden layers. Now, we sort of defined what a deep network is. Why do we need to use it, though? That's the big question. Why deep learning? Why just not a neural network, for example, or simply a linear predictor? And the motivation, as I said earlier, is that it does this feature selection for you. And in some problem, it was shown that these hidden layers can act like an abstraction of your input to get some sophisticated transformation between x and y. One example is if you take an image as an input, and the image is made of pixels, so x is made of pixels. Each one of the entries of x is simply the color of each pixel. And then it was shown by some papers that the first hidden layer will capture the edges of that image. The second hidden layer will capture main features of your face, for example, the eyes, the nose, the mouth, the ears, etc. And then once you get towards the end of the network, you start capturing bigger features of the face. And so it's becoming more and more abstract, this representation of the input, until at the end you can make a useful prediction, which is y hat. For example, I'll give you a rough example. Let's say your phone that recognizes your face. It takes in an image, and the image is simply a set of pixels, and it has to abstract that set of pixels to decide whether it's you or not. And if it's you, then y hat will be 1. If it's not, it will be 0. Most probably, it will be something between 0 and 1, so it's a probability. If it finds that with high probability, the person in front of the camera is you, then it will open, it will unlock your phone. If not, it will keep it closed. But you can see that this is something you cannot do with linear predictors because it doesn't make sense to come up with the feature vector yourself. For example, the edges of eyebrows, the edges of eyelashes, things that you cannot actually code yourself. So it makes sense to use a very nonlinear function that maps an image to a yes or no answer. And this is really the motivation of deep learning, which is feature learning. You learn the features. The algorithm learns the features on its own. These images were taken from this paper, and this paper shows how each hidden layer represents level of abstraction in an image. Now, we will go through the normal topics of machine learning. What is the loss function? We want to find the best possible weights. Now we have matrices that are weights, W1, W2, W3, depending on how many layers we have. So what is our loss function, and how do we optimize that loss function? I'll take the simplest example, which is our neural network looks like this. We have one hidden layer, and therefore two matrices, W1 and W2. And our loss function will look something like this. We have inputs x, output y, and this is known output y. And the loss is simply the predictor minus y. This is a squared loss, and it's the predictor minus the actual value y squared, the L2 norm. Now we take this loss and we apply a stochastic gradient descent to it. To do that, we need to calculate the gradient. So the stochastic gradient descent update steps will look something like this. W1 is updated to be W1 minus the step size times the gradient with respect to W1 of the loss. And the same thing with respect to W2. And remember, these W1 and W2 are matrices that are made of fitting parameters, and we're trying to fit these parameters. We're trying to find the best parameters using stochastic gradient descent. Now, the big question is, how do you calculate these gradients? Well, you take this function, and you differentiate it with respect to W1 and W2. So how do you differentiate f with respect to W1 and W2? Well, you apply some calculus there, some chain rule. And the efficiency, the success of machine learning in recent years, well, deep learning. Deep learning has been around for a while. Neural networks are not new, but they only recently became efficient computationally. And part of that success is attributed to the algorithms that were discovered recently in the 80s and 90s for calculating these gradients efficiently. And of course, with the advent of the internet and therefore big data and fast computers, therefore fast computation, neural networks became much more practical in daily life. You can run a neural network on your computer. And now we have big GPUs that run neural networks with millions or billions of weights W. So how do we calculate these gradients is a very important part of why deep learning is successful. So I will go through that now. We, again, will define something called computation graphs. The idea of calculating gradients efficiently is to automate the calculation of gradients rather than doing it by hand. And to do that, we will define something called the computation graph. So let's say now we have some function. Z is equal to g of x, y. You have two inputs, x, y, and the output is z. Here, x, y, and are independent of the previous x, y's that I mentioned. So general function x, y gives z. The gradient of the output with respect to each of the inputs is given by dz dx. So this is the gradient of z with respect to x. And the gradient of z with respect to y is dz dy, all right? A partial derivative. And this is really calculating how, if I change the output, how the input would change. Let's take a simple example. If z is equal to simply the sum of x and y, then dz dx, the derivative of z with respect to x will be 1, and derivative of z with respect to y will be 1. If I do the same, for example, with multiplication, z equals xy, now the derivative of z with respect to x would be y, and dz dy will be x. Finally, this function doesn't have to have two inputs. It could have 3 or 4, or it could have only one input. So in the case of a one-input case, let's say z equals x squared. Now dz dx is simply 2x. So we defined this general idea of a computation graph. Let's make the problem a little more complicated. Let's say we have y is equal to g of x, and z is equal to h of y. So we have two functions, a composition of two functions, g and h, applied to the input x. Now we can represent like this. X goes to y through the function g, and y goes to z through the function h. What is the derivative of z with respect to x? This is the question. And to get the, if you know the chain rule, to get dz dx, you need to apply the chain rule. It's dz dy times dy dx. But in this computational graph representation, this is simply like this. You calculate dz dy, and you calculate dy dx. And all you need to do to get dz dx is to multiply these arrows. to go through the green arrows back from z to x. So this is going to be dz dx equals dz dy times dy dx. All right, so what if y is equal to x squared and z equals to y squared? Now, this is one example. How would you do it? Again, you would do the same thing. Now dz dy is equal to 2y, and dy dx is 2x. If you do that, you get 4xy. Now you replace the value of y in 4xy, and you get 4x cubed. All right, this is where we get to backpropagation. Backpropagation is this process that makes neural networks efficient, and that was discovered in the 80s. And we're going to take now a much more complicated function, which will be our loss function. And we want to calculate the gradient of the loss function with respect to w1 and w2, our weights. So the loss function looks something like this. This is our predictor minus the true values y. And we start from the input x. We multiply it by w1, and we get to s1, the score. This sum, we define the output to be s1. Now, we take s1, and we pass it through this nonlinear function sigma, and we get v. This is our hidden layer v. At each stage, we get the derivative of s1 with respect to w1 is x, and the derivative of v with respect to s1 is, in this case, v dot 1 minus v. This is the Hadamard product. It's an element-wise product of the vectors v and 1 minus v. And the reason I get this gradient is because I assumed my sigma to be a sigmoid function, just for this example. A nonlinear function doesn't have to be sigmoid. It can be any nonlinear function, as I mentioned earlier. So in this case, it's v 1 minus v. Then I take this v, and I multiply it by w2, and I get s2. S2, the gradient of s2 with respect to v and s2 with respect to w2 are given by w2 and v. You can keep doing that at every stage. Of course, what I'm doing is basically calculating this loss function at every stage. And s2 is goes through sigma and gives me y hat. Now y hat is basically this prediction shown by this function. Okay, and now to get to the loss, I need to take y hat minus y and square it. So I take y hat minus y. I get the residual, and the residual with respect to y hat, the gradient with respect to y hat is 1. And finally, I square the residual to get the loss. And now the gradient of the loss with respect to the residual is 2r. What's the point of building this whole graph? The point is, now I want to calculate the gradient of the loss with respect to w1, shown here, and with respect to w2, shown here. OK? How do you do that? Now it's very simple. All you need to do is multiply all the green arrows going back from L to W1 and L to W2. In the case of W1, you have to do gradients of L with respect to W1. So I multiplied 2r by 1 by y hat dot 1 minus y hat by W2 by v dot 1 minus v by x. Of course, this multiplication is not trivial when matrices are involved. So you have to be careful that the matrices match and you're multiplying matrices in the right order. But the general idea is simple. You just multiply back all your individual gradients. And this is really just an application of the chain rule. The same thing happens with the gradient of L with respect to W2. So this is backpropagation. And now that we have an automated way of calculating gradients, sophisticated algorithms or packages for deep learning implement this sort of structure. They build the graph that has the computation of the neural network. And because everything is represented in terms of a graph, the gradient is also easy to calculate and can be done efficiently. Now we take this, we go back to defining our loss. What is the training loss? It takes this individual loss of individual training examples, xy, and it gets the average. The training loss is the average loss over all the training data. The objective is to simply minimize the training loss with respect to W1 and W2. And this minimization is done using stochastic gradient descent. And once we get our best weights, W1 hat and W2 hat, we plug it back into the optimal predictor, and we get this predictor FW1 hat, W2 hat. Of course, here I'm assuming that we have one hidden layer. In the case where we have many hidden layers, you can imagine we have many more of these matrices, W1 and W2. Will be Wn, where n is, 1 plus the number of hidden layers, something like that. Correct me if I'm wrong. All right. So we're trying to minimize this loss function. And as we explained last time, the loss function in the case of linear predictor looks like a paraboloid. And all we need to do is initialize the w's to some value. And then we go down this paraboloid to the minimum. In the case of a nonlinear predictor like a neural network, this will be slightly different, because our function is not convex. So we might have many minima. And it's very easy in this case to get stuck in local minima, especially that our w's are now, we have so many weights. And the function LTrain will be very high dimensional and will have a lot of local minima. And in fact, this makes this optimization problem very hard and very non-convex. And in reality, there are many reasons why neural networks shouldn't work because of this problem of having non-convexity. But in practice, there are a lot of tricks that you can use to avoid getting stuck in these local minima. And these are very important also to make neural networks work. If we go back to our concept of hypothesis class, again, assuming that I just have one hidden layer, this is my predictor. And my hypothesis class looks something like this now. It's FW1, W2, X, such that W1 is in this high dimensional real space, K by N, and W2 is in M by K. Here, K and N are just integers. So the hypothesis class is part of these larger all predictor class. But you can imagine, because neural networks are very nonlinear, they're nonlinear in W, in the weights, and they're nonlinear in X, they can represent very complex functions. And you can see in application, these complex functions could be, for example, mapping one language to another, used in translation of languages. It could be mapping an image to a name. Or it could be even mapping a sentence to an image, reconstructing an image from a sentence. So you have these very complex mappings that takes something that doesn't look like the output. It's really hard to visualize them, but neural networks can represent these complex mappings. And that's the case because the hypothesis class of a neural network or a deep network is very large. And therefore, it manages to reduce this approximation error even for very complex tasks. So the approximation error is very small in neural networks, depending on your task, but it does really well with approximation. The problem, however, is the estimation error. Now that you have a bigger hypothesis class, it becomes much harder to get to the optimal solution, FW1 bar, FW2 bar. In fact, you will get to FW hat, W1 hat, and FW2 hat. And that will be very different from the actual optimal solution in your hypothesis class. And the biggest challenge in neural networks is to, again, find tricks to get closer and closer to your FW1 bar and W2 bar, and therefore reducing your estimation error. Now, to address this question, how do you address this challenge of reducing the estimation error? The idea first is you want to put many hidden layers. This will actually reduce your approximation error by making your function more complex. You want to use adaptive time steps for your stochastic gradient descent. And this will also will help you avoid getting stuck in local minima. And finally, you want to use some sort of hyperparameter optimization in neural networks because there are a lot of hyperparameters. One of the biggest hyperparameters is the number of layers. Then there is the dimension of the layers. And there are, for example, different choices of the activation function. These alone have so many combinations that are not part of your stochastic gradient descent, but that are things you want to optimize over. You want to find the best network that solves your problem. And remember, when you're doing hyperparameter optimization, that you want to use your validation set, not your test set. So you start with your training set, you get your gradients, and then you apply, once you get to the optimal solution, you apply the loss, you calculate the loss on the validation set, and then you go back and you change your hyperparameters and you retrain your model. Once you're done, you go back to your test set and see if your model generalizes. Now, here I cannot show you the show you how neural networks work, but I really encourage you to go to this TensorFlow website, playground.tensorflow.org, that allows you to play with neural nets and show you how, for examples of classification or regression, show you how adding layers affects your prediction. It shows you, it allows you to choose different activation functions and shows you what each layer is actually doing. It can visualize what each layer and each node is actually doing. So I encourage you to do that, and it'll help you gain intuition about neural networks. Now, I got this from this link below, and in fact, neural networks, the idea of a neural network is really to connect nodes in linear and nonlinear ways so that you can perform certain tasks. There are certain tasks, for example, that require very deep networks. There are certain tasks that require you to have feedback in the network where the output feeds back into the input. And there are tasks, depending on the task you're trying to achieve, you can design a different network. And you can see there's sort of a zoo of neural networks. And it really depends on the problem you're trying to solve. So you can go to that website and really see how you can construct neural networks. If you remember from the last video, I said that scientists in the Renaissance, the art of science was really about constructing an experiment to find a linear relationship between two measurable quantities. And with neural networks, the art is to construct a neural network that can solve your problem. And in that sense, neural networks tend to be very experimental, where you have a lot of hyperparameters, and you have to be smart about choosing your architecture and your loss function. And by adding things to your loss function, you can constrain your network to do certain tasks. But it is using neural networks is very experimental in nature, because you don't know beforehand what you want your hidden layers to do, and you expect your network to discover these hidden features on its own. But that's not always the case. In the real world, what you will get is a hidden layer that doesn't really represent what you're expecting. And sometimes the hidden layer is not interpretable, so you run into this problem of interpretability of neural networks. So the key here is to be careful about all these details and to try as many networks as possible depending on your problem. I will just mention a few neural nets that are common in the literature and that are useful. Autoencoders, again, going back to this simplified image of a neural network, you can imagine here also you can have many layers. So I have an input x, a hidden layer v, and output y hat, the prediction y hat. And now I want to simply define the loss to be the prediction fw1, w2x, and subtract the input x. So what I want my network to do is to first compress x into some lower dimensional v, and then reconstruct x from this lower dimension v. So now here y hat is, in fact, I want y hat to be x. And this part is called an encoder because it reduces the dimension from 3 to 2. And then the second part is called a decoder from 2 to 3. It goes from 2 to 3. And here you don't have to have only one layer. You can have multiple layers. For example, you can imagine having 5 dimensions here, then 3, then 2, and then 2 goes to 3, and then 5. This low dimension V now acts as a latent space representation, a compression of your input x. So let's say x is an image, and you want to compress it into a lower resolution image. This is one way to think about it. But you can think about it also as you want to extract some important features of the image. For example, if you want to know whether it's a cat or a dog, you want to maybe compress your image to just give you what is important in the image, transform it, for example, into a word. A word is lower dimensional than an image. And in fact, if you choose the sigma to be, or if you remove the sigma, or sigma as this identity, if you make it an identity matrix or an identity function, then you recover something similar to the SVD decomposition. It becomes equivalent to the SVD decomposition, which is the singular value decomposition. And this should be SV decomposition. And this is actually given by x equals u sigma v star. You can look for SVD decomposition, or also similar to PCA. And PCA is similar to autoencoders, but it does this compression projection on a lower dimensional space in a linear space, in a linear fashion. There are also convolutional neural networks. Convolutional neural networks are, they usually apply to images where you want to find local patterns in the image. So it takes a 2D image, a 2D matrix, and it applies a filter to locally to this image to find the relationship between the adjacent pixels. And by doing so, it sort of finds local patterns. For example, if you're trying to detect whether there is a cat or a dog in your image, it doesn't matter where the cat or a dog is in the image. You just want to know, for example, the form of the face or the adjacent features. And so in this case, you use something called the convolution filter. And this convolution filter tells you how to combine the pixels next to each other. And now you get another matrix, which is not the image, but a post-processed image that multiplies the filter by the local patch of the image and sums all the terms, like this. Also, convolutional neural networks are very successful in detecting images. The example I showed earlier for image classification or for detecting whether it's you on the camera of your phone or not, all probably use convolutional neural networks. And in practice, also convolutional neural networks use many layers of abstraction, where the first layer will do some sort of convolution. This is called the convolution operation. And then there is pooling, convolution, pooling. Pooling will basically also try to compress your image into a lower dimension. And at the end, you get something very simple where it says, well, tell me what this car is, or what the brand of the car is. I got this from this link, which is also has a good introduction to convolutional neural networks. Now, recurrent neural networks are also neural networks that deal with series or sequential data, where you have, for example, time-dependent data given by x1, x2, x3, up to xn. And this time-dependent data, you know that the previous time step will cause the next time step, or any time step will depend on the previous time step. Then you construct this neural network that tells you that it takes an input xi and it returns xi plus 1, the next time step. It can also take some other unrelated input y and return z with it. So xi and xi plus 1 don't have to be the only inputs and outputs. The general representation of a recurrent neural network would be something like this. It takes in xi and it returns xi plus 1. So you train it to predict the next time step. Let's say you have a physical model and you want to integrate it in time, and you have a state xi at a given point in time, and you want to predict xi plus 1. So you use a recurrent neural network where you take in xi, it predicts xi plus 1, and then you use that xi plus 1 as an input in the next time step and predict xi plus 2, etc. And of course, you can have as many whatever inputs and whatever outputs you want. So you can append xi to something else like yi that doesn't really accumulate in time or is not part of your integration. Now, this is very common, for example, in learning flow maps. Let's say you have some time series, a dynamical system, and in fact, numerical solvers that solve PDEs and ODEs are recurrence relations. And recurrent neural networks will learn recurrence relations from data for you. OK, so now that I made that was a quick overview of what neural networks are and different examples of what neural networks can look like. And so I will conclude with this general procedure of applying machine learning and deep learning problems to data. So you have your data set, you split it in 3, you visualize your training set, and you see how it looks like. And based on that, you choose what the architecture of your data is. And in fact, in a lot of machine learning problems, you will spend a lot of your time on data cleaning, dimensionality reduction, unsupervised metrics, like, for example, compressing your data to lower dimensional space, using SVD decomposition. So a bulk of your time will go onto cleaning the data. In fact, maybe 80%. Depending on the problem, it will be more than 50%. And only a smaller part of your problem will be to apply your deep learning or machine learning problem, because there are packages out there that can do that for you. And again, you define what your feature input is. In the case of deep learning, you might want to try to just throw in your inputs as they are and hope that the hidden layers will discover the features for you. You do the hyperparameter tuning. You run your optimization algorithm, and then you come back and test it on your validation set. Once you test it and you're not satisfied, you go back. And in this loop, you can do your hyperparameter optimization by changing your hyperparameters t, eta, and lambda, and of course, the number of layers, number of hidden layers. There are so many knobs in deep learning that you can change that can improve your model. And once you're done, you come back and you test it on your test set. So this is the general idea of deep learning. And of course, it's an active area of research. People are applying these methods to different problems, and there are always advances in this field. So if you have suggestions or ideas about deep learning in general, or you have comments about this video, please add comments below. And see you next time. Thanks.